Hello, juniors. This is electronic assignment number 14. We're going to cover the topic transforming functions. So basically what we're going to be studying today is the different types of transformations that any type of function may undergo. Okay? So the objective for this class is to understand the different types of transformation of graphs. So we're going to mainly cover three types of transformations which are covered in the IB program, which are translations, reflections, and stretches. We're going to try to understand what each of these transformations mean by looking at an example I prepared using the application Desmos. So this is the example. Imagine we have the parent function of a quadratic function, which is the red function you see in the graph, y equals x squared, okay? To the left, you may see all of the different functions that I'm going to graph. And to the right, you're going to see the actual graph of each of these functions. Okay, so the red function is a parent function for a parabola, right? It has its axis, its vertex, at point 0, 0. It's a happy face because the coefficient in front of the x squared is a positive number. And that's it, okay? So, what do you think the second graph will look like if I graph function number 2, which is x squared plus 2? What do you think should happen? If I graph this, you'll see that you get the blue graph over there, which is the same function as the red one, but it is translated 2 units upward, okay? So you see that when we get positive 2 or plus 2, the function moves 2 units upward, okay? Now, what do you think should happen for function number 3, where we have x plus 2 squared, when we have the plus 2 inside the parenthesis with the x? If you see this graph, you're going to see that the function moves 2 units to the left, right? So that sounds a little bit counterintuitive. We're going to see that in a while. But when we add plus 2 inside the parenthesis, the function actually moves left instead of moving right, okay? So pay attention to that. That's also a translation. For the first case, the blue function, we call that a vertical translation, 2 units upward. And for the second case, the green function, we call that a horizontal translation, 2 units to the left. Okay, what do you think should happen if I graph? I'm gonna erase the other two just for a second. What do you think should occur when I graph function number 4, negative x squared? What you're going to see is the following graph in purple. This is called a reflection. You see that the x-axis acts like a mirror over there, and we get the same quadratic function, but going in the opposite direction, okay? It's a reflection with respect to the x-axis. The x-axis is the mirror in this case. Okay, so that's what we call a reflection on the x-axis. Then, let's erase this one. What do you think should happen if when I plot function number 5, which is minus x plus 2 squared? I'm going to graph this one over here just for you to see the difference. If I graph this function, we're going to get this mirror over here. In this case, we're having a reflection, but a reflection with respect to the y-axis. In this case, the y-axis is acting like the mirror, okay? So we have two types of reflection on the x-axis, which was this case with respect to the red one, and with respect to the y-axis, which is the green function versus the black function, okay? So the y-axis acts like a mirror in this case. Then, going back to the parent function, what do you think should happen for the sixth function where we have 3x squared? Pay attention, we're going to get something like this. The dashed red function represents this transformation, which we call a stretch, a vertical stretch in this case, okay? So if you see the graph looks more compressed than the original function, and all of all of the values of y are tripled. We're gonna see that in a while, but if you look, let's see if we may identify, if you go to the point x equals -1, for example, you'll see that the red function is in 1, and for the red dashed function for x1, we should be at x equals 3. You see that? We're gonna do some examples later on in order to practice this concept. But this is called a vertical stretch, okay? And finally, for the last case, function number 7, I'm gonna graph this, and we get this blue dashed function, 3x squared. This is called a horizontal stretch, okay? And as example number 6, this also causes a compression of the original parent function, okay? So these are all the different types of transformations. Translations, which are these two over here. Then we have reflections, which are these two over here. Let me grab this one. And finally, we have horizontal or vertical stretches, okay? Which are in this case. These are all the different types of transformations we have, and that we're gonna study for the IB. Okay, so if we go back to the electronic assignment, we're gonna see this theoretical part. These are all the different types of transformations we just talked about. The first one, translations, in which we have two possible cases: a shift upward or downward, or a shift to the right or to the left. In order to have a shift upward, this should occur. It says f of x, or the function, plus k separated from the function. It says f of x plus k translates f of x vertically a distance of k units upward. And you see in this graph, for example, f of x is the original function, the red one, and f of x plus 1 is the original function, but translated 1 unit upward. You see that all of the points go up 1 place, okay? This point goes up 1 place, and so on. All of the different points of the function are translated 1 unit upwards, okay? Then the same thing happens for this case. F of x minus k translates f of x vertically a distance of k units downward. So in this case, we have the original function, which is the red one, this red one over here. So if we were to graph f of x minus 1, all of the points go downward 1 unit, right? 1 unit, and then we can graph the new function. Okay, then how do I shift to the right or to the left? It's this case. F of x plus k, it says translates f of x horizontally k units to the left. Pay attention to that. When it's plus k inside the parentheses, we're moving the function to the left. And when it's minus k, we're translating the function horizontally k units to the right, okay? You see a difference between the first case and the second case? In the first case, we have plus k outside the function, and in the second case, we have the k plus k adding inside the function where the x value goes, okay? So, same thing for this case. If we say f of x plus k, we're translating the function to the left. So, for example, this is the original function. F of x plus 2 would make all of the points translate 2 units to the left, right? So we're moving all of the points to the left. For example, this one moves 2 units over here, this one 2 units over here, and so on, okay? Same thing occurs for this case, but we're moving in this case to the right, right? So f of x minus 2 would make all the points move 2 units to the right. 2 units, 2 units, and so on. So those are the different types of translation, which is the first type of transformation. This is the easiest type of transformation. Okay. Then it says, a translation can be represented by vectors in the form AB. This is a vector. Whenever we write the components vertically, A, B, for example, 1, 2, this is a vector when we write the components vertically. Okay, so it says, in the form AB, where A is the horizontal component and B is the vertical component of the translation. And here's an example for you to understand this. You may see this in a real IB exam. That's why I'm showing you this. It says, translation by the vector 3, -2. If you see this, for example, translate a function using the vector 3, -2. What does that mean? It means that you should move the function horizontally 3 units to the right, because the 3 is positive, and 2 units down, because this is a -2, right? So this first value is for the horizontal translation, and this value over here is for the vertical translation. If it's positive, we're translating the function to the right, and if it's negative, or well, if the first component is positive, then we're moving to the right. If it's negative, we're moving to the left. And if the second component is positive, we're moving up. If the second component is negative, we're moving down. That's the rule for the translations given in the form of vectors. Okay. Then we have the second type of transformation, which is reflection. And it says, minus f of x reflects f of x in the x-axis, meaning that the x is acting like our mirror here, right? So if you see this function, the red one is the original function. So minus f of x, what would do is it would reflect the original function in the x-axis, meaning that all of the points, for example, this point we reflect it to using the x-axis, which means that we should change the sign of y. Okay, so if y, for example, here, if y had I don't know, this maybe 0.3, this point over here would be negative 0.3, and so on. We change the sign of all y coordinates. Okay, we're gonna see this in an example in a while. Okay, so that's minus f of x. Then we have the second case, which is f of minus x. You see the difference again? In the first case, we have the minus in front of the function, outside the function. And in the second case, we have the negative sign inside the function, and it's affecting the x. Okay? So in this case, f of minus x reflects f of x in the y-axis. So it has the same effect, but now the y-axis acts as a mirror, right? So you see, this is the original function, and the reflected function has its x-coordinates changed, okay? So you see that, for example, this point has the same y-coordinate as this point, but it has a negative, let's suppose this is 0.5, this would be negative 0.5. So all of the x-coordinates change sign, okay? Here, this is 1.5 for the x, so this would be negative 1.5 for the x, and so on, okay? That's reflection. And, okay, here's an example to see how reflection works. So before going to the third type of transformation, we're going to do a short example about this. Okay, so pay attention at this example. It says f of x, the function, is x cubed plus 2. So we're going to apply the different types of transformations given here, and then we're going to see how it actually should look like. Okay, so first of all, f of x. If I have a table here with the x values, how do I calculate the f of x? You know already that this is just replacing the x values into the function and then observing the result, right? So for example, f of negative 2 would be negative 2 cubed plus 2. And this gives us negative 8 plus 2, which is negative 6, okay? So this is negative 6. And then we can keep on doing the rest. This would be negative 1 plus 2, this is 1. 0 plus 2, this is 2. 1 plus 2 is 3. 2 cubed is 8 plus 2, 10. Okay? So we can plot these points into our function. The first point, negative 2, negative 6, would be negative 2, negative 6 is here. I'm going to erase this. Oop. Then negative 1, 1. Negative 1, 1 is here. Then we have 0, 2. 0, 2 is here. 1, 3 is here. And 2, 10 is here. Okay, so since this is not a straight line, we should graph this function without using a ruler, and we will get something like this. Kind of like that, okay? Then we're gonna build this function, which is minus f of x. What does minus f of x mean? It just means using the same values we got here, but changing its sign, putting a negative in front, okay? So I'm gonna do it with a different color. If, for example, this was negative 6, minus 6 would be positive 6, right? So this is 6. Then this would be negative 1, negative 2, negative 3, and negative 10. Okay? So now I plot these points using always this x-coordinate. So the first point would be negative 2 and 6. The second point would be negative 1, negative 1. And then the third point would be 0 and negative 2, and so on. Okay? So negative 2 and 6, that's around here. Then negative 1 is here. Then we have 0, negative 2. 0, negative 2 is here. Then we have 1, negative 3. That's here. And finally, 2 and negative 10 is... let's see. I need to extend this. Would be negative 8 and negative 10. Okay, so the point 2, negative 10 is here. So once again, we join these points without using a ruler, and we will get something like this. Do you see what happens with these two graphs? What type of transformation is this? This is called a reflection with respect to the x-axis, okay? The x-axis is acting as our mirror in this case. And you see that what we drew is function negative f of x. And according to our theory, negative f of x reflects f of x in the x-axis. That's exactly what happened in this example, okay? Okay, so now let's see what would happen if I first calculate negative f of x. I'm going to calculate those values. That means I just need to change the signs of the x, right? So this would be 2, 1, 0, negative 1, and negative 2. Now, what do you think should happen if I, for example, draw... let's see, if I want to draw this function, f of minus x. F of minus x. Let's make a column here for f of minus x. So, f of minus x. What should I do here? I should plug in into, let's do it with, or the group, no. Yeah, orange. I need to plug in these values of x into my function in order to get minus f of x, okay? So, the first value would be for 2. This would give me, you see that it's the same value as this one, so I'll get 10. Then I'll get 3, 2, 1, and negative 6. Okay? If I plug in those values. What will happen if I graph f of minus x? Remember, I should always graph with respect to these values of x over here. So negative 2 and 10 would be, let me erase this. Negative 2 and 10 is here. Negative 1 and 3 is here. Oh. Then 0 and 2 is here. 1 and 1 is here. And finally 2 and negative 6 is here. If I join these points by hand, we're gonna get a graph that looks like this. Okay, what type of reflection is it with respect to the original function, which is a red one? Let me put names to this. This is f of minus x. The red one is the original, which is f of x. And the blue one is minus f of x. So you see that the orange one is a reflection with respect to the y-axis. The y-axis in this case is acting as a mirror, okay? And what type of reflection according to the theory was f of minus x? It says f of minus x reflects the function in the y-axis. So that's exactly what we got in this example. Okay, I hope that reflection is clear now with this example. Okay, continuing with the last type of transformation, we're gonna see stretches. So, just like the other two cases, we have two types of stretches. The first one is what we call a horizontal stretch or compress, and it says f of qx stretches or compresses the function f of x horizontally with a scale factor of 1 over q. We're going to see that in an example, what exactly that means. And then we have vertical stretch or compress, and it says p f of x stretches the function f of x vertically with a scale factor of p. So you see the difference once again. In the first case we have the number affecting the x inside the function, and in the second case the p, which is any type of number, is outside the function. Okay, it's multiplying the whole function, and in this case the q is multiplying only the x. Okay, so it says here, it says a stretch with a scale factor p where p is between 0 and 1 will actually compress the graph. Okay, we're gonna see that with some examples in a while. So pay attention at these two cases. It says the transformation is a horizontal stretch of scale factor 1 over q. Why does it say 1 over q? Pay attention to this. If we have the original function, the red one, f of x, if I apply a horizontal, in this case, a stretch by a scale factor of 1 over 2, right, because we have a 2 over here, that means that all of the values of x will compress half of its value to half of its value. Okay, so for example, if this was 1.5, the new value for the compression would be 0.75, half of 1.5. Okay, or if we look at this value, this is 2, right? 2, half of 2 is 1, so the function, the blue one for that same point, is 1. Okay, so you see the compression here, right? For example, this 2.5 should be 1.25, which is this point over here. So all of the values of x are half of the original value. That's why it's called a horizontal compression. Okay, then the opposite thing occurs for the vertical stretch. You see that we have the original function, the red one, f of x, and when we write 2 f of x, you see the difference. In the first case we wrote f of 2x, in the second case we write 2 f of x. What this 2 outside the function is doing is it's multiplying, it's doubling, in this case, all of the values of y. So for example, if this was, let's say this is, I don't know, 0.3, the new value of the function of the blue one would be 0.6. It's double its value, okay? Or maybe, let me see, another point. This, which was the y coordinate is 1, it doubles, and the new value for the blue function goes to 2, okay? So all of the values of y are doubling in this case, instead of halving like in this case over here. In this case over here, okay? So the opposite occurs in each of these cases. So here it says, the transformation is a vertical stretch of scale factor p. When p is greater than 1, the graph stretches away from the x-axis, which is what is happening here, okay? But if the value of p is between 0 and 1, for example, 0.5 or 0.3 or whatever, the graph is compressed towards the x-axis. So it will be closer to the x-axis. And in this case, the opposite occurs. When q is greater than 1, the graph is compressed towards the y-axis. And when q is a value between 0 and 1, the graph is stretched away from the y-axis. It's exactly the opposite as this case. Okay, so let's see an example to see how this works, but it's basically the same process as the one we just did. So it says, f of x is x squared minus 2. This is our function. So we're gonna calculate each of these values for these values of x. Okay, so f of minus 2. F of minus 2 in this case would be, pay attention with the parentheses, minus 2 squared minus 2. And this gives us, this is 4 minus 2, 2. So this is 2. Then for negative 1, this would be 1 minus 2, which is negative 1. For 0, this is negative 2. For 1, this is negative 1 again. And for 2, this would be 2 squared, 4 minus 2, 2 again. Okay? So we can plot these points in our graph to get their first graph. So negative 2, 2 is here. Negative 1 and negative 1 is here. Then 0, negative 2 is here. 1, negative 1 here. And 2, 2 is here. What type of function is this? This is a quadratic function, right? And in this case, it should be a happy face. Why? Because the coefficient, which is a 1 over here, is positive, right? The coefficient in front of the x squared is positive. So if you see this function here, you'll see that it's the original parabola, the parent function, but translated 2 units downward, which is exactly what we observe in this graph if I join these points. We get a parabola, but shifted 2 units downward, okay? So that's the red function. Then we're going to calculate a second case. It says f of 2x. How do we calculate that? For example, f of 2 times 2, right? For times negative 2, sorry. Times negative 2. This would give us, this is the new value of x, which is the same as saying f of negative 4, right? 2 times negative 2 is negative 4. So we need to evaluate f of negative 4. This gives us negative 4 squared minus 2, according to our function. And this is 16 minus 2, 14. 14. So this is 14. And then we could keep on doing the same for the rest. In the second case, for example, this is 2 times negative 1. This is the same as saying f of negative 2. So this would be f of negative 2. We know it's 2, right? So this would be 2. This is 2. Then for 0, this would still be f of 0. So this would be negative 2. For 1 positive, this would be 2 because we know it's a parabola. And for 2, this would be 2 squared, 14 again, right? So we're going to plot these points, and we're going to see what happens. So for -2, we're at 14. 14. For -1, we're at 2. For 0, we're at -2. For 1, we're at 2. Here. And for 2, we're at 14. So we join these points. Kind of like this. What do we get? We get a parabola once again, but this is compressed, right? It has compressed towards the y-axis, right? It is now closer to the y-axis than the values we had over here. So what do we have? A vertical compression, a horizontal compression towards the y-axis, okay? So this is f of 2x. The function compresses towards the y-axis. And then to calculate 2f of x, what do we need to do to calculate 2f of x? It's just multiplying these values of x we got of f of x we got here times 2, okay? So we're going to do this using blue. So this would be 4, double this would be -2, then -4, -2, and 4. Now we're going to plug in these values. Remember, it's always with respect to these values of x. So the first point would be -2, 4. -2 and 4 is here. -1 and -2 is here. 0, -4 is here. 1 and -2, 1, -2 is here. 2 and 4 is here. So if we join these points, by hand, we're gonna get kind of this function, okay? So in this case, let me check this. That's better. Okay, so in this case, it's kind of hard to see what we get, but this is it is also a compression. No, it's not a compression, it's a stretch with respect to the x-axis, meaning that it moves away from the x-axis. You see that all the points double. This was a 2 over here, and now it's a 4 for the y. And this point over here, which was -1, now turns to be -2, and so on. So you see that all the values are doubled for the function, and this makes the blue function move away from the x-axis, which is this axis over here. This is y, this is x. Yes. Okay, so we're getting this case. When p is greater than 1, the graph stretches away from the x-axis, okay? The blue function is further away from the x-axis with respect to the red function, okay? Let's read these observations, which will help you understand a little bit better how stretches work. This third case, stretch, is definitely the hardest type of transformation. It's usually the one that students struggle more understanding what's actually happening. So it says, observation number 1. In the case of the horizontal stretch, f of qx, which is the first case we saw here, the height stays the same, but each point gets closer to the y-axis half as much when q equals 2. The invariant point is x equals 0. The invariant point which we're talking about is, if you look at the graph, you see that for x equals 0, The green function is in the same place as the red function, okay? That's why we call the invariant point. It's a point that doesn't change. Then, observation 2. In the case of a vertical stretch, Pf of x, each value of y doubles the original value of y if p equals 2. The invariant point or points is y equals 0. Why are we talking about points? Because it'll be multiple points if the function crosses y equals 0 in multiple times, okay? Which is this case, for example. In this case, you see that y0 corresponds to this point over here and to this point over here. And you see that in both points, the blue function is crossing, the blue function shares the same point with the red function. They are crossing in the same point, okay? So that's, in this case, we have two invariant points, okay? So I hope these observations made it a little bit clearer for stretches. Okay, now that we've seen all the different types of transformations, we're gonna see one example in which we're gonna see how all of the different types of transformation work, okay? So in this graph over here, we have something called a piecewise function. Why is it called a piecewise function? Because it behaves differently in each of the intervals, okay? So from 0 to x equals 2, it behaves as a linear function with a positive slope, right? From 2 to 4, the function behaves as a straight line, but it's a horizontal line, so slope is 0 in this case. And finally, for this interval over here, from 4 to 6, it behaves again as a straight line with a positive slope, and it's the same slope as this one, so we can say that this line is parallel to this line, okay? So that's what we call a piecewise function. In Spanish, this is called función a trozos. Okay, so it says, given the graph of the function f of x, which is a piecewise function shown here, sketch these graphs. So we have a, b, c, d, e, and f. We're going to sketch all of these graphs using different colors for you to understand what each of these transformations imply, okay? So, let's start by re-sketching the original function f of x. So we have this point 0, 0, 2, 2, then we have 4, 2 here, and 6, 4, 6, 4 here. So if we join these points, we're gonna get the same graph, this one over here. So let's graph the first function, part A, which is f of x plus 1. What should we do if we're asked to find f of x plus 1? Remember, this is a horizontal translation, which is 1 unit to the left, meaning that all of the points should move 1 unit to the left, okay? So we identify all of the points of the function, this for example, and we move it 1 unit to the left, okay? Because it's f of x plus 1. So this point over here moves here. This point, the second point moves here, 1 unit, okay? The third point moves here, and the fourth point moves here. All of the points move 1 unit to the left. Then we join these points, and we get the blue function, which is the same. You see that the shape is exactly the same, but it is translated 1 unit to the left. Then, part B, f of x minus 2. What type of transformation is this? This is a vertical transformation, which moves the function 2 units down, because there's a negative sign in front of the 2, right? So we need to translate the original function, the red one, 2 units down. So in this case, all of the points move 2 units down. So the first point, this one, moves 2 units down. So it moves here. Then the second point moves here. The third point moves here, 2 units down, and the fourth point moves here. Okay? Then we join these points and we get the function, which once again has the same shape as the original function, but it is translated, all of the points are translated to units down. Okay, then we have part C, which is f of minus x. If you remember from the transformations, this minus x means that all of the values of x would change the sign. And what do you think should happen if we change the sign of x? We're having a reflection with respect to the y-axis. So pay attention. This point, for example, has coordinates 0, 0. So if we change the sign of the x, it will still be the same point, right? It will be 0, 0. So this is like an invariant point for this particular exercise, okay? Then if I write the coordinates of this second point, this one over here, this has coordinates 2, 2. When we try to find f of minus x, what we're gonna do is we're gonna change the sign of the x coordinates. So this would be negative 2, 2. So that point is over here, right? And we're gonna do the same for all of the points. For example, this point over here has coordinates 4, 2. So for the reflection, this would have coordinates negative 4 and 2. Negative 4 and 2 is here. Okay? So finally, for the last point, which has coordinates 6 and 4, this would be at negative 6 and 4. It'll be here. So you see that we get the same graph. It has the same shape, but it is reflected with respect to the y-axis, okay? The y-axis acts like a mirror in this case. So that's f of minus x. Then we have f of minus x, negative f of x, which basically means change the signs of y, okay? Change the sign of y. So in this case, we change the sign of x, and in this case, we change the sign of y. Okay, so what do you think should happen to the original function if I change the coordinates of y? We're going to have a reflection on the x-axis. So now the x-axis will act as a mirror, okay? So let's do this. Minus f of x, that means changing the y coordinate. So the first point, which is 0, 0, will still be 0, 0. The second point, which is 2, 2, would now be 2, negative 2. We're changing the y coordinate. So this point would be here. And then we do the same thing for all of the other points of the graph. This point over here, remember it's 4, 2. So the reflection would be 4, 2. 4, 2 is here. And finally, this point is 6, 4. So this would be 6 and negative 4 over here. If we join these points, we're going to get the graph, which has this same shape, but now it's reflected with respect to the x-axis, okay? The x-axis acts as a mirror here. Okay, then part E. I don't know what color I used there. This one. It says 2f of x. When we're asked to find 2f of x, what we need to do here, this is like saying 2y. And this means double each of the values of y, okay? So that's exactly what we're going to do. We're going to double all of the values of y. So this point over here, the first one had coordinates 0, 0. So if we multiply 0 by 2, we're still getting 0. So this is an invariant point. So we're having the point here. For this point we had over here, which is 2, 2, the new point for this transformation would have coordinates 2, the x remains the same, but the y should be doubled, right? So this would be 2, 4. That'll be the new point. So 2, 4 is a new point, 2, 4 here. And we do the same thing for all of the points. This point had coordinates 4, 2. Now we have coordinates 4, 4 because we double the y coordinate. And finally, 6, 4 would go to 6, 8 here. So you see that we get this function over here, which is, this doesn't have the same shape as the original function, and rather it is stretched with respect to the x-axis, okay? It moves away from the x-axis. All of the points are doubled in this case because we have a 2 here. If we had a 3, we would triple all of the points, all of the y coordinates, and so on, okay? So this is called a vertical stretch. Finally, for this case, this is f of 2x. Let's see if I have the brown over here, this one. What do you think should happen here? This is a horizontal compress. This means that the brown function that we're going to graph should be more compressed or closer to the y-axis than the original red function. Okay, so what do we need to do to graph f of 2x? We need to halve each of the values of x. So, for example, the first point, which is 0, 0, once again is an invariant point because 0 divided by 2 is still 0. But then for this point, once again, this is 2, 2. The new point for this function would be 1, 2. We need to halve this value. 2 divided by 2 is 1, okay? So the new point is 1 and 2. 1, 2, so it'll come here, right? Then this point is 4, 2, so it'll come to 2, 2. It'll be here. And finally, this point, which is 6, 4, would now be 3, 4. 3, 4, which is here. So if we join these points, you'll see that we'll get a function that has a different shape from the original function, and it is compressed towards the y-axis, okay? You see that the red one is the original, and the brown one is the compressed function, and it moves towards the y-axis, okay? So these are all the different transformations reflected in one exercise. Okay, so I hope this is clear enough for you. You're gonna practice later on with tons of exercises about this in order to really understand all of the different types of transformations. Okay, then we have this case, which we're gonna read and analyze only. I'm not gonna solve all of the exercise. It says functions g is the blue one. I'm gonna put it with color. G, you see G, blue one. R is the kind of orange one. And S, N is green, are transformations of the graph of f, which is kind of this color. Find the functions g, r, and s in terms of f. So in this case, we don't know we only have the graphs of the functions, and we now want to determine what transformations were applied in order to get each of these functions, okay? So pay attention, the original function is always f in this case, which is a w here, okay? So how do you think we can obtain the function g from the graph of f? What I see is that here we have a horizontal stretch, right? In order to have a horizontal stretch, I remember that it's this case f of qx, where q should be a number between 0 and 1 in order to make a stretch, okay? Remember that f of 2x made a compression towards the y-axis. So, for example, f of 1/2 x would make a horizontal stretch, okay, which is what I want for this exercise. So I know that gx is some number which is between 0 and 1. And you see that all of the values, for example, this -2 over here, now, sorry, not -2, -1 over here, now moves to -4, which is the vertex of the W, right? So the horizontal compression, horizontal stretch, sorry, would be 1/4, because we're multiplying all of the values of x by 4, okay? Quadruple its value. So let's read the explanation. It says gx is f of 1/4 of x, which is exactly the same analysis I did. And here it says, the graph of g is a horizontal stretch of the graph of f with a scale factor 4. So 1 over q equals 4, so q equals 1/4. Okay. Then, let's determine function r. You see that r has the same shape as the original function f, but there are 3 transformations here. The function is translated first an amount of units to the left, then it is reflected, because you see that here we have a w, but this is an m, right? So it is reflected with respect to the x-axis, and finally it is shifted upwards a certain amount of units, okay? So there are 3 transformations in order to get the function f to a function r, okay? So let's see the transformation. It says r of x is minus f of x plus 4 plus 5, it says. And the explanation says, the graph of r can be obtained by translating the graph of f 4 units. So you see that all of the points, this point moves 1, 2, 3, 4. 4 units to the left, okay? This point, 1, 2, 3, 4 here, okay? So 4 units to the left, all of the points. Then reflecting in the x-axis in order to get the m, right, instead of the w. And then translating up 5 units. You see that all of the points, for example, this one, goes up 5 units. 1, 2, 3, 4, 5, and we go to the top, right? So all of the points are shifted or translated 5 units upward. So that's why we get this graph over here, this function over here. Minus f of x, what that does is the reflection on the x-axis, right? That's why we see a negative sign in front. Then plus 4 is what makes a horizontal translation 4 units to the left. And this plus 5 over here outside of the function is a vertical translation 5 units up. Okay, so there are 3 types of transformation in this case. Finally, for function s, we see that we have the same, not the same shape, but the same letter. We still have w here, but once again we have both a horizontal translation and also a vertical translation, because the w moves upward. And there's also a vertical stretch, because the w is more stretched than the original w we had over here, right? So once again, 2 types of translations, horizontal and vertical, and a vertical stretch. So we get this function over here, which is s of x equals 2f of x minus 5 plus 4. And it says, the graph of g can be obtained, no, the graph of s should actually say here. It should be an s. Let's make a little change here. The graph of s. S can be obtained by translating the graph of f right 5 units. You see that all points move to the right 5 units. For example, this one 1, 2, 3, 4, 5, and we get to this point over here. We're moving 2 units up, right? 5 to the right, 2 units up. So 5 to the right, 4 units up. Yes, because there's a vertical stretch later on. So 5 units to the right, that's why it's -5. Then it says a vertical stretch with scale factor 2. Why scale factor of 2? Because all of the points double. For example, let me see. If we move, let me see. If we calculate the distance from this is 8 to 0, right, to the bottom, and in this case it's from 2 to -2. So there's a distance of 4 here, while there's a distance of 8 here. So that means that all of the values of the W are doubled, right? That's why we have the 2 over here. All of the values double. And then the +4, it says vertical stretching with a scale factor 2 and translating up 4 units. All of the points are translated 4 units, okay? So I'm going to leave this to you. If you want to analyze this more in depth, you can read this and try to understand it better. But this is a tough example where you are also going to practice with some of these exercises in order to really understand what transformations are. Okay, so finally, this is a brief summary of all of the different transformations that you're going to see for the IB. We have reflection on the x-axis, which is y equals -f of x. Reflection on the y-axis, which is y equals f of -x. Vertical dilation, which is the same as stretch or compress with a scale factor of absolute value of a. When we say vertical stretch or compress, we put the value in front of the function. When we say horizontal dilation or stretch or compress, we put the number in front of the x inside the function. And finally, vertical translation. Vertical, when we add or subtract a number outside the function. And horizontal translation, when we add or subtract a number inside the function, affecting the x value, okay? And then here's a screenshot of all of the different transformations we've seen at the beginning of the class. This is for you to try to remember all of these types of transformation. It is very important to clarify that these transformations are not in the formula booklet. So I'm going to write this here. Not in the formula booklet, meaning that you should memorize or really try to understand these transformations because you won't have them in the formula booklet, okay? So really practice and understand these transformations, and if you understand this well, why each of these transformations look like they look, you wouldn't have much struggle with this topic, okay? So that's it, juniors. This was kind of a long class, but I hope you could understand this clearly, and if you have any doubts, you can always ask.